Hello everyone, and welcome back to Econ Explorers. The importance and intrigue of what's hidden beneath the ice of Antarctica lie in the profound scientific discoveries and their broader implications. Here are some key points to explain the significance. Climate change records. The ice in Antarctica preserves a detailed record of Earth's climate history. Ice cores extracted from these regions provide scientists with invaluable data on past temperature variations, atmospheric composition, and greenhouse gas levels. This information is crucial for understanding climate change and making informed decisions about our planet's future. Geological insights. Antarctica's bedrock contains fossils and geological evidence that offer insights into Earth's ancient history. Studying these fossils and rock formations can help researchers understand the evolution of life on our planet and the breakup of the supercontinent Gondwana. Extraterrestrial clues. Antarctica is a treasure trove for meteorites that fall from space. These pristine samples can provide insights into the composition of celestial bodies, helping scientists learn more about our solar system's origins and the potential for life elsewhere in the universe. Extreme ecosystems. The discovery of subglacial ecosystems in Antarctica's hidden lakes has challenged our understanding of life's adaptability. These extremophiles thrive in conditions previously thought to be inhospitable, sparking interest in the search for life on other planets with extreme environments. Ocean dynamics. Antarctica's underwater canyons and mountain ranges impact ocean circulation, which, in turn, affects global climate patterns. Studying these seafloor features is essential for understanding how the oceans and climate are interconnected. International cooperation. Antarctica is a continent of international collaboration for scientific research. It serves as a model for peaceful cooperation among nations, fostering goodwill and advancing our collective knowledge of Earth and the universe. Subglacial lakes. Subglacial lakes are a unique and intriguing feature of Antarctica, and one of the most notable among them is Lake Vostok. Let's explore the concept of subglacial lakes with a focus on Lake Vostok. 1. What are subglacial lakes? Subglacial lakes are bodies of water that exist beneath the massive ice sheets of Antarctica. These lakes are isolated from the external environment by the overlying ice, which can be several kilometers thick. 2. Discovery of Lake Vostok. Lake Vostok is one of the largest and most famous subglacial lakes in Antarctica. It was discovered in the 1990s using remote sensing techniques and radar surveys that revealed a massive body of liquid water beneath the East Antarctic ice sheet. 3. Extreme isolation. Lake Vostok has been isolated from the outside world for millions of years. The isolation, extreme pressure, and sub-freezing temperatures have created an environment with unique properties. 4. Scientific significance. Lake Vostok is of great scientific interest due to its potential as an analog for extraterrestrial environments like the ice-covered oceans of Europa, a moon of Jupiter. It provides insights into the limits of life's adaptability in extreme conditions. 5. Subglacial exploration. Scientists have been working on drilling into Lake Vostok to directly sample its waters and investigate the microbial life it may harbor. The drilling process is challenging, as it requires preventing contamination of the pristine lake and maintaining the integrity of the ice core. 6. Microbial discoveries. Despite the challenges, research has yielded insights into microbial life in the accretion ice above Lake Vostok. These extremophiles have evolved to survive in the unique conditions of subglacial lakes. 7. Future research. Ongoing and future research at Lake Vostok and other subglacial lakes aims to further our understanding of these hidden ecosystems. Scientists hope to answer questions about the lake's origins, its potential habitability, and the implications for astrobiology. Underwater canyons and mountain ranges. Antarctica's seafloor features a fascinating and unique topography that is of great scientific interest. Here are some key points to discuss the intriguing aspects of Antarctica's seafloor. Underwater canyons. Antarctica's seafloor is not the flat, featureless expanse one might imagine. It is, in fact, home to deep underwater canyons, some of which are larger and deeper than the Grand Canyon. These canyons can reach depths of thousands of meters and have been shaped by ancient glacial processes. submarine ridges and mountain ranges. Alongside the canyons, Antarctica's seafloor also boasts submerged mountain ranges and ridges. The most prominent of these is the East Antarctic Ridge, which stretches for thousands of kilometers. These underwater geological features play a crucial role in influencing ocean circulation patterns. Ancient history. The geological history of Antarctica's seafloor is intertwined with the continent's formation. Antarctica was once part of the supercontinent Gondwana, and the seafloor holds evidence of this geological history. Fossils of ancient marine life, once connected to the continent, can be found here. Ice-ocean interactions. The seafloor plays a significant role in the interaction between Antarctica's ice sheets and the surrounding ocean. Warm ocean water can melt the ice shelves from below, causing them to thin and potentially contribute to sea level rise. Understanding the topography of the seafloor is critical for predicting how ice sheets may respond to climate change. Influence on global climate. The features of the seafloor can affect ocean circulation patterns, which, in turn, have a global impact on climate. Changes in these patterns can alter the distribution of heat around the planet, affecting weather systems and potentially influencing long-term climate trends. Scientific exploration. Antarctica's underwater landscape is an area of active scientific exploration. Submersibles and remotely operated vehicles, ROVs, are used to study this remote environment, allowing scientists to collect data, images, and samples from the seafloor. Protection of ecosystems. Understanding the seafloor's ecology is also essential for preserving the unique marine life in the Southern Ocean. These ecosystems are adapted to extreme cold and darkness and are particularly vulnerable to environmental changes. The features of Antarctica's seafloor, such as underwater canyons, mountain ranges, and ridges, have a significant impact on ocean circulation and ice behavior. Understanding their role is crucial for comprehending the complex interactions in this region. Here's an explanation of their significance. 1. Influence on ocean circulation. Blocking and channeling flow. The underwater canyons and ridges act as barriers and channels for ocean currents. They can redirect the flow of water, causing it to be funneled through certain areas while hindering it in others. Vertical mixing. The topography can induce vertical mixing of ocean waters. When strong currents encounter undersea ridges or canyons, they are forced to change depth, leading to mixing of different water layers. This mixing has consequences for heat distribution and nutrient transport in the ocean. Thermohaline circulation. The seafloor's influence on ocean circulation includes its role in the thermohaline circulation, or the global conveyor belt. The sinking and upwelling of dense, cold, and salty water at high latitudes are vital components of this circulation, which helps distribute heat around the planet. 2. Impact on ice behavior. Melt and thinning of ice shelves. The topography of the seafloor plays a crucial role in the interaction between ice shelves and the ocean. Warm ocean water can penetrate beneath ice shelves through underwater channels created by the seafloor features. This can lead to the melting and thinning of the ice shelves from below, making them vulnerable to climate change. Influence on glacier flow. Submarine ridges can affect the flow of glaciers that terminate in the ocean. They can act as pinning points, slowing down the glacier's movement. Alternatively, undersea canyons may provide pathways for glaciers to flow more rapidly into the ocean. Feedback loops. Changes in ocean circulation and the behavior of ice can create feedback loops. For example, as ice shelves thin due to warm water, the ice behind them may flow faster, contributing to sea level rise. Understanding these feedback mechanisms is crucial for predicting the consequences of climate change in the polar regions. Sea level implications. The interaction between the seafloor and ice behavior is directly related to sea level rise. The retreat of ice shelves and the acceleration of glaciers into the ocean can contribute to rising sea levels, which have global implications for coastal communities. Fossils and ancient life. The discovery of fossils and evidence of ancient life in Antarctica's bedrock provides valuable insights into the continent's geological history and its role in Earth's ancient ecosystems. Here's a showcase of some key discoveries and their significance. 1. Fossils in the Transantarctic Mountains. In the Transantarctic Mountains, fossils of ancient marine life have been found, dating back to the time when Antarctica was part of the supercontinent Gondwana. These fossils include remnants of trilobites, brachiopods, and other organisms that lived in the region over 500 million years ago. The presence of these fossils indicates that Antarctica once had a much milder climate and was home to diverse marine ecosystems. 2. Plant fossils in the Beardmore Glacier region. Plant fossils have been discovered in the Beardmore Glacier region of Antarctica, shedding light on the continent's terrestrial history. These plant fossils, including remnants of trees and ferns, suggest that Antarctica was once a forested environment during the late Permian period, approximately 250 million years ago. The existence of these plant fossils provides crucial evidence for the ancient flora of Antarctica and its connection to other southern land masses. 3. Marine reptiles and dinosaurs. Fossils of marine reptiles and dinosaurs have been found in Antarctica, further revealing the continent's prehistoric past. These discoveries include the remains of plesiosaurs, ichthyosaurs, and sauropod dinosaurs. These findings help paleontologists understand the diversity of life in Antarctica during the Mesozoic era and its role in the broader context of Earth's history. 4. Insights into climate change. Antarctica's fossil record offers insights into the effects of climate change over geological timescales. The transition from a more temperate climate to the extreme cold of Antarctica is documented in the fossil record. By studying these ancient ecosystems, scientists can draw parallels with current climate change and its potential impacts on Earth's biodiversity. 5. Connection to Gondwana. Antarctica's fossil evidence contributes to our understanding of the supercontinent Gondwana, which included present-day Antarctica, South America, Africa, Australia, India, and other land masses. Fossils found in Antarctica align with those from other Gondwanan land masses, providing evidence of the continent's geological history and its past connections to neighboring regions. 6. Ongoing discoveries. Antarctic expeditions and scientific research continue to uncover new fossils and evidence of ancient life, expanding our knowledge of the continent's distant past. These discoveries are made possible by advancements in technology, such as improved mapping, drilling, and fossil extraction techniques. Meteorites. The collection of meteorites in Antarctica is a fascinating and important aspect of space science. Antarctica's unique characteristics make it an ideal location for recovering meteorites, and these extraterrestrial rocks offer valuable insights into the composition of space objects and the history of our solar system. Here's an exploration of this topic. 1. Pristine preservation. Antarctica's icy environment helps preserve meteorites in a pristine condition. The cold temperatures and lack of moisture prevent weathering and contamination, making it an excellent collector of meteorites. 2. High discovery rate. Antarctica has yielded a high rate of meteorite discoveries. Every year, researchers find hundreds of meteorites on the ice, making it one of the most prolific sources of meteoritic material on Earth. 3. Diverse meteorite types. Antarctica hosts a wide variety of meteorite types, including chondrites, echondrites, irons, and carbonaceous chondrites. This diversity allows scientists to study different types of meteorites and gain insights into the composition of various celestial bodies. 4. Understanding solar system formation. Meteorites are remnants of materials from the early solar system. By analyzing meteorites, scientists can gain valuable information about the processes that led to the formation of planets and other celestial bodies. 5. Cometary and asteroidal material. Some meteorites contain material that originated from comets or asteroids. These meteorites are essential for understanding the building blocks of our solar system and the origins of water and organic molecules on Earth. 6. Clues to planetary formation. The study of meteorites from different parent bodies provides insights into planetary formation and differentiation processes. They help answer questions about the internal structure and composition of planets and asteroids. 7. Implications for astrobiology. Carbonaceous chondrites, a type of meteorite found in Antarctica, contain organic compounds. This has implications for astrobiology, as these meteorites may carry the building blocks of life or provide insights into the origins of life on Earth. 8. Scientific collaboration. Antarctic meteorite recovery is a collaborative effort involving scientists from around the world. This cooperation fosters international collaboration in space science and planetary exploration. 9. Space missions and sample return. Understanding meteorites in Antarctica can inform the design of space missions. For instance, the collection of meteorites can help researchers develop plans for the return of samples from other celestial bodies, such as asteroids or Mars. Ice cores and climate history. Ice cores are invaluable tools for scientists to uncover Earth's climate history. These long cylinders of ice drilled from polar ice sheets and glaciers provide a chronological record of past climate conditions, offering insights into temperature variations, atmospheric composition, and major climatic events. Here's a discussion of how ice cores reveal Earth's climate history. 1. Accumulation of snow and ice. Over thousands of years, snow accumulates in polar regions, gradually compacting into ice. Each year, a new layer of snow adds to the previous layers, preserving a chronological record. 2. Trapped air bubbles. As snow compacts into ice, it traps tiny air bubbles. These bubbles contain samples of the atmosphere from the time the snow fell. Analyzing the composition of these ancient air bubbles provides insights into past atmospheric conditions, including greenhouse gas concentrations. 3. Isotopic analysis. The isotopic composition of water in ice cores can reveal temperature variations. The ratio of heavy to light isotopes, e.g., oxygen 18 to oxygen 16, in the ice is a proxy for past temperatures. 4. Chemistry of ice. The chemical composition of ice can provide information about past volcanic eruptions, forest fires, and even the history of pollution. Elements and chemical compounds are preserved in ice, and their concentrations can be analyzed. 5. Dust and aerosols. Ice cores contain layers of dust and aerosols from the atmosphere. These layers can be used to identify major volcanic eruptions, which can have significant short-term climate impacts. 6. Dating and chronology. The annual layering of ice, combined with other dating methods like radiocarbon dating, helps establish a precise chronology for the ice core. This dating allows scientists to correlate events in the ice core with other historical records and make accurate comparisons. 7. Glacial and interglacial cycles. Ice cores reveal the waxing and waning of ice sheets over the past several 100,000 years, demonstrating the existence of glacial and interglacial cycles. They provide data on the timing and magnitude of these cycles. 8. Climate change and variability. Ice cores help document past climate change and variability, including abrupt climate events. They provide essential data for understanding how the climate has responded to natural and anthropogenic factors. 9. Implications for future climate. By studying Earth's past climate through ice cores, scientists can make more informed predictions about future climate change and its potential impacts on the planet. Research stations. Research stations in Antarctica play a crucial role in supporting scientific studies and exploration in one of the most challenging and remote environments on Earth. These stations are vital hubs for research and provide essential infrastructure for various scientific disciplines. Here's an overview of research stations and their vital role. 1. Location and distribution. Antarctica is home to numerous research stations operated by different countries. They are strategically located across the continent to provide comprehensive coverage for scientific investigations. 2. Logistics support. Research stations offer logistics support for scientists and their equipment. They provide a base of operations for fieldwork, including transportation, accommodation, and facilities for scientific experiments. 3. Interdisciplinary research. These stations host scientists from various disciplines, including glaciology, climate science, biology, geology, and astronomy. Interdisciplinary collaboration is fostered, enabling comprehensive research. 4. Climate and weather monitoring. Many research stations in Antarctica are equipped with climate and weather monitoring instruments. They collect data on temperature, atmospheric conditions, and other climate-related parameters. 5. Glaciological studies. Stations support research on glaciology, including ice core drilling and the study of ice sheets and glaciers. This research helps scientists understand past and future climate changes. 6. Biological and ecological studies. Researchers at these stations study the unique ecosystems of Antarctica, including seabirds, seals, and extremophiles. They examine how these organisms adapt to extreme conditions. 7. Geological and seismological research. Stations support geological studies, including the examination of rock formations and fossils. They also contribute to seismological research to monitor geological activity. 8. Astronomical observations. Antarctica's pristine skies make it an ideal location for astronomical observations. Some research stations have observatories for studying celestial phenomena. 9. Environmental monitoring. Stations participate in environmental monitoring programs to assess the impact of human activities in Antarctica. This helps ensure that research is conducted in an environmentally responsible manner. 10. Collaboration and data sharing. International cooperation is a fundamental aspect of research stations. Scientists from various countries collaborate on research projects and share data to advance scientific knowledge. If you're intrigued by the fascinating world of science and exploration, and you want to stay informed about the latest discoveries and adventures, consider subscribing to our channel. By subscribing, you'll be part of a community of curious minds, always eager to explore the wonders of our world and beyond. Subscribing is a simple way to show your support for the work we do, and it ensures that you won't miss any of our exciting content. We're dedicated to bringing you the latest insights, discoveries, and stories from the frontiers of science and exploration. So, click that subscribe button, ring the notification bell, and join us on this incredible journey of discovery. Together, we'll continue to explore the mysteries of our planet and the universe, one fascinating topic at a time. Thank you for being a part of our scientific and exploratory community.